All right, so here is section 7.2, and we're talking about integration using substitution. And we use substitution in the case where we have definite or indefinite integrals, where it isn't a straightforward, easier way to just go ahead and integrate the problem. Like in the first set of problems that we saw in 7.1, you had like power functions, basic exponential functions that you could, just separate and just apply basic integration techniques. However, in order to apply that technique in an instance like problem number one, well, number one, you'd have to FOIL this expression out and multiply it by itself 8 times, and that would just take too long, and that's a little bit impractical for what we're trying to achieve. So what we use is a method called substitution, and that's what we're going to be walking through in some of these examples. So I'll go through the first few pretty much from start to finish, and then once we kind of get the hang of it, then I'll just go ahead and show you guys how to set up the substitution, and then you can just complete the rest of it on your own, because then you'll just be back to using the basic integration techniques. So starting with number one, you see once again you would have to FOIL this out to just apply the regular power rule. So you want to use substitution, and the key to using substitution is correctly identifying what you want to substitute in the problem. And normally it's just an expression that's in the problem that seems like it's a little bit more complicated. And in this case, we're going to substitute, and we're going to say u equals 7x minus 9. So we'll be taking this 7x minus 9 and replacing it with u. But notice in this problem, and it is taking an integral with respect to x. So if we're substituting the x out, then we can't integrate it unless we substitute and take this dx out as well. So if u equals 7x minus 9, then we can say du equals 7 dx. So we took the derivative of this equation with respect to x. So the x just became dx. This is du now. So now we'll make our substitution from the original problem with u instead of x's. So this will now become u to the 8th power du. And notice that at first there was a 7 here, but notice that du equals 7 and dx. So when we substitute the du into the equation, that's taking the place of this 7 and this dx. So now it's a pretty straightforward integral where we can just apply the power rule to complete it from here. So we're taking the integral of u to the 8th power. So this will become 1 over 9 u to the 9th power plus c. And for our final answer, we just go ahead and we substitute back in for u. So this will be 1 over 9 times 7x minus 9 to the 9th power plus c. And here is our antiderivative. Now, for number 2, we have 10 over 2x plus 5 to the 6th power. So here we're going to say, well, u can equal 2x plus 5. So du equals 2 dx. Now, notice that there is no 2 dx in this problem to easily substitute for in this. So now is where it starts to take a little bit of practice to kind of get used to making these substitutions. And as you do more and more, it'll be a little bit smoother. So since there is no 2 dx in the problem, there is a dx, but we're going to substitute for dx. So we'll get the dx by itself in our equation here. So 1/2 du, or we could say du over 2 equals dx. So we'll take out dx, and in its place we'll put 1/2 du. So going back to the problem now, this equals the integral of 10 over u to the 6th power times 1/2 du. And now we can simplify this, and then we'll be able to find the antiderivative. So this will be, so 10 over 2 will just be 5 u to the negative 6 du. Now we can use our power rule. So this will be negative 5 over 5 u to the negative 5 plus c, and the 5s will cancel. So we'll be left with, once we substitute back in 2x plus 5 for u, we'll have 2x plus 5 to the negative 5th power plus c. Sorry, negative, because the 5's cancel, but you still have the negative sign there in front. And remember, if you're not sure if you did everything right, once you get to your final step, to check your answer, all you do is take the derivative of your answer. So we took the derivative of this, the negative 5 would come down, so then it would be positive 5 times 2x plus 5 to the negative 6, and then you would have to multiply times 2, making that 5 become a 10. So this is our answer. Now, moving on to number 3. As you can see, it looks a little bit more complicated, but again, as long as you could choose the correct value for u, you'll be fine. So in this case, let's say u will be the more complicated expression. We'll say u equals 14 x squared plus 36x. So du will equal 28x plus 36 dx. So now, let's see, can we factor anything? Because it doesn't quite match this expression that we have up here, where it's 7x plus 9. But let's see if we can factor it to reduce it a little bit. So we'll say du equals 4 times 7x plus 9 dx. And this lets us know we're on the right track, because now we see we have the 7x plus 9, we have the dx, but we also have a 4 here that is not necessary. So we'll move the 4 over to the left side, so we know we're taking 1/4 du, and we'll substitute that for 7x plus 9 dx. So we'll take out the 7x plus 9, we'll take out dx, and we'll put 1/4 du in its place, and then this will just become u to the negative 5th power. So this equals 1/4 u to the negative 5 du. So again, 1/4 du, the 1/4 du took the place of 7x plus 9 dx. So that was this part. And then we let u equal this expression in parentheses, and it was raised to the 5th power in the denominator, so we made it u raised to the negative 5th power here. And now we find the antiderivative. So this will be 1/4 times 1 over negative 4 u to the negative 4 plus c. So this will be negative 1 over 16, and then we'll substitute back in for u, so we'll plug 14x squared plus 36x back into the equation, raised to the negative 4th power plus c. Now for number 4, we have 24t to the 5th power times e to the negative t to the 6th power dt. So here we may not be exactly sure what we want to use for u, so we can check both of them and see which one seems like it would help us a little bit more. So first we'll try u equals 24t to the 5th power. So in that case, du would be 120 t to the fourth power. And that doesn't immediately strike us as something that we can make substitutions for just based on the way that the problem is written here. So then let's check to see what happens if we let u equal e to the negative t to the sixth power. Well, in this case, du will equal negative 6t to the fifth power times e to the negative t to the sixth power. So we look back at our equation here and we see that we do notice that we have t to the fifth power in the equation, and we also have e to the negative t to the sixth power. But we don't see the negative 6, so we can move the negative 6 over to the left side. So we'll divide both sides by negative 6, so we'll have negative 1 over 6 du equals t to the fifth power e to the negative t to the sixth power. Oh, and we're missing the dt. So dt. So all of this expression, t to the fifth power e to the negative t to the sixth, dt will all be substituted for negative 1 over 6 du. So here we'll substitute now this expression, and the dt. So we'll have 24 times negative 1 over 6 du. And notice that now we don't see any variable here. And let's simplify it. So this equals negative 24 divided by 6 is going to be negative 4 du. So this is just a constant function. So when we take the antiderivative, this will be negative 4u plus c. And just to check, remember, if you take the derivative of negative 4u, that will leave you with negative 4. U will go away, and that will be du. So now we just need to substitute back in for our u. So now we have negative 4, and u is e to the negative t to the 6th. So e to the negative t to the 6th power plus c. And there is our answer. So again, it's not always obvious until you practice a little bit more what you want your u to be. So sometimes it helps if you just check and let u be different things and see where that gets you once you look back at making the substitution in the original problem. So now, number 5 is similar. So I'll show you how to just make the setup, and then you can finish it from there. So similar to like we just saw with number 4, let's say we'll let u be the exponential expression, e to the negative t to the third power. So then du will be negative 3t to the second power, e to the negative t third dt. So then we'll make our substitution. It looks like we have t squared, we have e to the negative t to the third, and we have dt, but we have this negative 3 here, so we'll move it away. So negative 1/3 du equals, and this is what we're going to end up substituting out of the equation. So then this will equal the 4 stays, and we have t squared, the e to the negative t to the third dt, all being substituted out and replaced with negative 1/3 du. And then from there, it is very similar to the way that we did number 4 previously. So now, moving on to number 6. Again, it's not immediately obvious, but the way that the past couple problems have been working, it looks like it will be helpful if we let u be equal to our exponential expression, so e to the x squared plus 2x. So then du will equal, and in this case we keep be an exponential expression because the base is e to the x squared plus 2x times 2x plus 2. And if we factor it, we can take out a 2, so this will be left with x plus 1. So let's see, du equals 2 times x plus 1 times e to the x squared plus 2x. And again, missing the dx here. So dx comes at the end of these. So now we don't have a 2 that's in this expression, so we don't need the 2 on the right side to substitute in. So we'll put 1/2 du, because we're dividing both sides by 2 here, and that equals x plus 1 e to the x squared plus 2x dx. So now we'll substitute everything out for 1/2 du. So all of this equals integral of 1/2 du. And then we integrate, and remember to substitute u back in after you find your integral and simplify it. All right, so now we have a rational function, radical function, and an exponential function. So we have a lot of different options that we can choose from in terms of what we want u to equal. In this case, and as you've probably seen in the last previous examples, it may be a good idea to just try to see what happens if we let u equal e to the 9 square root of y. So we'll just let u be the entire exponential function. Another option we could have gone with, we could have said, well, u is equal to square root of y, or u equals 9 times the square root of y. But in this case, we'll just let u equal e to the 9 square root of y. So now our derivative of u is going to be still e to the 9 square root of y, and then times the derivative of our exponent, which would be 9 times 1/2 y to the negative 1/2. So let's clean this up a little bit. So du equals 9 over 2 square root of y, and also we'll have e to the 9 square root of y dy. So let's see. In terms of our original problem, we see that we have the e to the 9 square root of y over square root of y dy. We just don't need the 9/2. So we'll multiply by 2 over 9. And then we can make a total substitution for everything that's in the problem. E to the 9 square root of y over the square root of y dy. So this will become the integral of 2 over 9 du, because the du is substituting in for this entire expression that we have here. So then from there, this will equal 2 over 9 u plus c, and then we can go back and complete the substitution and just simplify everything out. So this will finally be 2 over 9, and we already said u is e to the 9 square root of y, so e to the 9 square root of y plus c. Our next problem, we have a quotient, and notice that in the denominator now is where the terms are separated by an addition sign, so we can't just separate this problem like we did in some of our previous exercises in 7.1. We cannot put 16x to the third power over 5 plus 16x to the third power over x to the fourth. That's not how it works. In this case, again, we have to use substitution. So let's just try and say u equals 5 plus 4x to the fourth power. So du will equal 16x to the third power dx. And from here, it's obvious we can make our substitution directly. 16x cubed is dx. will be substituted for the du, and then this will just be u to the negative first power. So this equals integral u to the negative first power. We're taking the 5 plus 4x to the fourth, and we're just raising it to the negative first power because it was in the denominator, du, and then we use our simple rule here. This will be, since it's 1 over u, that will become ln absolute value of u plus c, and we said u equals 5 plus 4x to the fourth plus c. And in this case, we don't need the absolute values because 4x to the fourth power will always be positive anyway. No matter what you plug into it, it's always going to give you a positive value. Or even if you plug in 0, it will just be 0, but you're still adding 5 to whatever this value is either way. So this is the same as ln, and we don't need the absolute value. We can just use normal parentheses 5 plus 4x to the fourth power plus c. So now for number 10, let's see, we have a radical function. We can say u equals just the argument here. Just let u be the radicand, the t to the fourth plus 5t. So du will equal 4t to the third plus 5 dt. So then we can rewrite our integral as the integral of, this will now be u to the 1/2 times d. And then we go ahead and finish working that out. Number 11, we have 1 plus 2 ln x raised to the 11th power over x dx. So let's say we allow u to be our argument again here. Let's let u be our base this time. So u equals 1 plus 2 ln x du will equal, the 1 will change to 0, the 2 will stay, and we'll have 1 over x dx. So you see we have an x in the denominator, we have a dx that we want to get replaced out, but there's nothing we can do with the 2 here, so we'll make it 1/2 du to be substituted in for 1 over x dx, and that will take care of this x in the denominator and that dx. So this becomes the integral of u to the 11th power times 1/2 du. And we could have just written the 1/2 up front, but just to keep it consistent so you see what we're substituting in and out. And then the next step we'll go ahead and do that. So 1/2 u to the 11th power du. And then from there, you are going to find the antiderivative. Remember to add c. Remember to go back and substitute it in 1 plus 2 ln x for your value of u. Number 12, we have 9e to the 9y over 6 plus e to the 9y. So here it looks a little bit tricky. Should we let u be the numerator or the denominator? We're not sure. Let's just try each one out. So let's see what happens if we let u be equal to the numerator first. That will be 9e to the 9y. So then du will be 9e to the 9y times 9. So du in this case will be 81e to the 9y. If we let u equals 9e to the 9y. So then we would have u here, we'd have a dy here, but we still can't easily see how we would get rid of the e to the 9y. So it can be done, but let's see if it might make a little bit more sense to just let u be equal to our denominator. So this time u equals 6 plus e to the 9y. And then we're actually going to end up with the almost the same derivative. We'll have du equals the 6 will become 0, and then we'll just have 9e to the 9y dy. So this looks like it'll go a little bit smoother if we let u equal the denominator. Why? Because u will take the place of this entire denominator, and then du will take place of both the 9e, 9y, and the dy here. So in this case, it'll be a little bit easier if we just go ahead and make the u substitution for the denominator instead of the numerator. We could have continued with the numerator, but it would have taken a little bit more work. The substitution wouldn't have been quite as smooth. So we're taking out 9e to the 9y dy and replacing that with du. So here we'll have du replacing all of this, and this is getting replaced with u. So we have du over u, or if it's a little bit more easier to see, you can write it as 1 over u times du, and still you can write that as the integral of u to the negative first power du. And then from here, you take the antiderivative, we're going to have ln absolute value of u plus c, u equals 6 plus e to the 9y. So this would be ln 6 plus e to the 9y plus c. And again, we have another case where we could actually not use the absolute value symbol because e raised to a power is always going to be positive, and we're adding 6 to it anyway, so this will always be positive, so you could go ahead and use the parentheses. If you're typing your answers into Math Excel, it'll take your solutions either way with the parentheses or with the absolute value symbols, so you can use either or in that case. All right, now looking at our applications. It says a population grows at a rate of p prime of t equals 300 t e to the negative t squared over 8, where p of t is the population after 2 months. So we're looking for a formula for the population size, given that the population is 5,000 when the time is 0. So first of all, our population function is going to be the antiderivative of our growth rate function. So this would be 300 t e to the negative t squared over 8 dt. So we'll need to do a u substitution. So let's say u equals e to the negative t squared over 8. So then in that case, du will equal negative 1 over 4 t e to the negative t squared. And this is just from taking the derivative of this expression here, over 8 dt. And this is just from our derivative up here. So you know the e to the negative t squared over 8 will stay, and then you have to multiply by the derivative of this exponential expression. So that would leave us with negative 1 over 8 times 2t, which became negative 1 over 4t. So now we can substitute out the t, we can substitute out the exponential expression on the dt, but we still have a negative 1/4 here. So we'll move that to the left side before we substitute. So negative 4 du equals this expression, t e negative t squared over 8 dt. So we'll substitute this expression and take out this expression. So this equals integral of 300, and now we put negative 4 du in there. So this equals integral of negative 1200 du. So that means our function, our population function, is going to be negative 1200 u, and we'll substitute back in e to the negative t squared over 8 for u. So this will be negative 1200 e to the negative t squared over 8 plus c, and that is our population function. So now we need to solve for c. They tell us that the population when t equals 0 is 5,000, so we know the 0 is going to be 5,000, and that's going to equal negative 1200 e to the negative t squared. Oh, sorry, negative 0 squared, because we're plugging in 0 for t, over 8 plus c. So then this will be 1. So we'll add 1200. So our c equals 6200. Then if c equals 6200, now our actual equation comes from here. So p of t equals, and I'll just write it out, negative 1200 negative t squared over 8 plus 6200. So now in our next step, they ask us to use the formula to find the population after 2 months. So then we're just plugging in 2 into our equation, and that's going to leave us with approximately 286.25 when we plug it all in, and we're rounding to the nearest person in this case, so that will be 286 people. Number 14 says you have an epidemic growing in a region. How fitting. An epidemic is growing in a region according to the growth rate formula that's given 76t over t squared plus 2, where the n of t function is the number of people infected after t days. So find the formula given that 62 people were infected when t is 0. So again, we're going to have to find an antiderivative of 76t over t squared plus 2 dt. And in this case, we need to use substitution again. So let's say u equals t squared plus 2. So then du will equal 2t dt. So we have a t, we have dt that we can substitute out, but we don't have any place to put the 2, so we'll move it. We'll substitute it, and so we'll have 1/2 du equals t dt. So now our integral will be 76, and that's over u, and then t dt became 1/2 du. The t dt equals 1/2 du. So then we can simplify this expression a little bit. Let's make this 76 divided by 2 will be 38 u to the negative first power du. So our antiderivative then for our n function, n of t, will be equal to 38 times ln of u plus c, and u equals t squared plus 2. Again, t squared plus 2 will always be positive, so we can drop our absolute value once we substitute that in. So this equals 38 ln of t squared plus 2 plus c. Now we need to figure out what c is. So since they tell us when t is 0, when t is 0, our function value is 62. We're going to say 62 equals 38 ln of 0 squared plus 2 plus c. So then we'll have to subtract on this side. So 62 minus 38 ln of 2 equals c. And we'll go ahead and punch that in. We end up getting c is approximately going to be 35.660. So now our equation from here, we can substitute in for c now. So this equation is going to be n of t equals 38 ln t squared plus 2 plus 35.66. Then our last step, now we just need to plug in 27. So we're looking for n of 27, and that's going to leave us with 286. Just a small note from our previous problem for number 13. I realized that it was odd that I got 286 twice. When you plug 2 into this function, you're actually supposed to get 5,472, which makes a whole lot more sense given that the population was 5,000 to begin with.